Section 3.4 is all about properties of rational functions. Friendly reminder that at the end of this PowerPoint, which is up on Blackboard, I have multiple step-by-step workout examples of how to find asymptotes. That's going to be our key takeaway from Section 3.4. Also for this section, you're going to need to know polynomial division. I have two videos. One is on standard polynomial division. Another one is on synthetic. These are videos I made for another course, but will work in a little refresher on polynomial division. We're going to need that to find oblique asymptotes, which we'll talk about shortly. Friendly reminder that a rational function is defined by a quotient, quotient's another word for fraction, of polynomials, and has the form f of x equals p over x over qx, where q of x doesn't equal 0. The domain of our rational function is all real numbers except those that make our denominator equal to 0. And this is something we have talked about earlier in the course, and it's because we cannot divide by 0. Where we would divide by 0 is where we get what x values would make our denominator 0 give us vertical asymptotes. There are also two other types of asymptotes we could have, horizontal asymptotes and oblique asymptotes. What an asymptote is it's a line that our curve, that our rational function approaches but will never cross, and it keeps heading on and on towards infinity. For example, here's the reciprocal function, y equals 1 over x. It has a vertical asymptote at x equals 0, because my denominator could ever equal 0. This also has a horizontal asymptote at y equals 0, because my numerator could never equal 0. It's also of lesser degree than my denominator, which we're going to talk about. Another really basic example of a rational function is the graph of y equals 1 over x squared. It has a vertical asymptote at x equals 0, again because our denominator cannot equal 0. And it also has a horizontal asymptote at y equals 0, again because my numerator can never equal 0. When I have a multiplicity in my denominator that is odd, my end behavior goes in opposite directions of our asymptote. If I have an even multiplicity of a function, for example, if I had 1 over x squared, x equals 0, had a multiplicity of 2, my end behavior goes in the same direction along my vertical asymptote at that point. There's a nice little paragraph summarizing what I just said. So, how do we determine asymptotes? So the first thing you always want to do is find your vertical asymptotes. You do that by setting your denominator equal to 0. These are going to be your vertical asymptotes. After that, you have to check for three different types of asymptotes. Horizontal equals 0, horizontal equals a constant, and oblique. If you meet the qualifications for A, you don't need to check the others. If you meet the qualifications for B, you don't have to check the others. If your numerator has lesser degree than the denominator, then there is a horizontal asymptote at y equals 0. So if your function's bigger on bottom, y equals 0. If the numerator and the denominator have exponents of the same degree, then the functions of the form f of x equals a sub n over b sub n, and so on and so forth. And your horizontal asymptote is at y equals a sub n over b sub n. So if they have the exact same degree, you divide the constants. If the numerator is of degree exactly 1 more than our denominator, so if I had a numerator degree 3 and a denominator degree 2, that's when I would have an oblique or a slanted asymptote, and its equation is going to be a linear equation. My coworker gave me this interesting acronym initialism. Okay, so here's the asymptote rules abridged. I will be giving you this chart right here on exams and quizzes, but you have to make sure you know how to use them. So first off, for horizontal is Bobo. Bobo Boatin eats DC, that's what she said. So Bobo stands for bigger on bottom. So if I have a bigger degree in my denominator, y equals 0. Boatin means if I have a bigger degree on top, so my numerator, then there's none. There's no horizontal no horizontal asymptote. Eats DC is if the exponents are the same, divide constants. I don't know how helpful this is. Thank you, Debbie, for suggesting it. But you'll have to let me know, students, what you think. For your vertical asymptotes, always set the denominator equal to 0, and for oblique, you use division if degree of the numerator is the degree of the denominator plus 1. So why don't we practice finding some asymptotes and then graphing a couple of rational functions. So for example 1, the first thing we do is look for our vertical asymptotes, and we do that by setting our denominator equal to 0. So we want to look for our vertical asymptotes first. I subtract 1 from both sides. 2x equals -1, x equals -1/3. So I have a vertical asymptote at x equals -1/3. I then check for my horizontal asymptotes. So if it's bigger on bottom, so if the degree is bigger on bottom, i.e. the numerator has lesser degree than the denominator, then there's a horizontal asymptote at y equals 0. Once I've met that criteria, I don't need to check to see if they have the same degree, so it's a constant, or if there's an oblique asymptote. So those are my two asymptotes. Next, to find my vertical asymptotes, I set my denominator equal to 0. I then use the zero factor property to find the two vertical asymptotes I'm going to have, which is totally okay. I get x equals 1/4 and x equals -5. Those are my two vertical asymptotes. I then go ahead and see, okay, is the numerator lesser degree than the denominator? Well, yeah, the numerator is degree 1, but our denominator is going to be degree 2. If I FOIL this out, you can see it's degree 2. So I also have a horizontal asymptote at y equals 0. Next, to find my vertical asymptotes, step 1, I set my denominator equal to 0. So I have 4x minus 6 equals 0. That gives me that 4x equals 6, so x equals 6/4, which is 3/2. This is my vertical asymptote. I then go for my horizontal asymptotes. If my numerator is lesser degree to my denominator, well, my numerators are of same degree. If they are the exponents are the same degree, that's when you divide constants. That's the eats DC part of my friend's acronym. Horizontal asymptote is y equals a over b. So I have a horizontal asymptote at y equals 2/4, which is y equals 1/2. So that's my horizontal asymptote and my vertical asymptote. Next, I have x squared plus 1 over x minus 3. To find my vertical asymptote, I set my denominator equal to 0. I get a vertical asymptote at x equals 3. I then look for my other asymptotes. If my numerator is of lesser degree than the denominator, then there's a horizontal asymptote at y equals 0. While my numerator is of greater degree, so it's not going to be a. Because my numerator is of greater degree, they aren't going to have the same degree, so it's not going to be b. The only option left is none, which could happen, or oblique. If my numerator is of degree exactly 1 more than my denominator, then there's an oblique asymptote. Well, this just happens to be the case. So now I divide my numerator by the denominator and disregard the remainder. So I'm going to use long form division because it makes me happy. Notice I put a placeholder in for x. That's what you have to do. If you aren't comfortable dividing polynomials, please go back and review the videos I have suggested. So what do I multiply x by to make it look like x squared? Well, that's x. X times x is x squared. X times negative 3 is negative 3x. We subtract. That gives me 3x, pull down a factor of 1. What do I multiply x by to make it look like 3x? Well, that's going to be 3. 3x minus 9. Subtract that. We get a remainder of 10, and I disregard the remainder. So I have an oblique asymptote at y equals x plus 3. It's always going to be a line because its degree is one more than the denominator. Now why don't we go ahead and graph some of these? So we're going to state our domain, zeros, and asymptotes. Well, we found earlier that this has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals negative 1/3. So here's my vertical asymptote. Here's my horizontal asymptote. My domain is all real numbers except where x equals negative 1/3. My range is all real numbers except where y equals 0 because my graph can't cross that. It's not going to have any x-intercepts, right? It can't have any x-intercepts because it can never cross the x-axis where y is 0. So no x-intercepts. But it could have a y-intercept. So our y-intercept is when x is 0. So if I plug in 0, f of 0 equals 2 over 3 over 0 plus 1, which is 2. So that's my y-intercept. And x is 0, y is 2. So my graph's going to look something like this. It's a multiplicity of 1, so the end behavior is opposite. Let's graph one more. Okay, let's graph two more. So I found a vertical asymptote at x equals 3/2 and a horizontal asymptote at y equals 1/2. So here's my vertical asymptote. Here's my horizontal asymptote, x equals y equals 1/2. That's where my graph cannot cross. To find my y-intercepts, I let x equal 0. F of 0 equals 0 over 4 times 0 minus 6, which just gives us 0. So here's my y-intercept when x is 0, y is 0. In order to find my y-intercept, in order to find my x-intercept, I let y equal 0. So I have 0 equals 2x over 4x minus 6. So I will find that x equals 0. So our origin is our x-intercept and our y-intercept. And that's okay. My graph, because the denominator has an odd multiplicity, is going to look like this. And please, take some rational functions, graph them in Desmos, see how it'll help you visualize what's going on. Last but not least, let's graph x squared plus 1 over x minus 3. I had an oblique asymptote at y equals x plus 3 and a horizontal asymptote. I didn't have one of those, but I had a vertical asymptote at x equals 3. The multiplicity of our denominator is odd. Here's my oblique asymptote. So to find my y-intercept, I let x equal 0. So I get f of 0 equals 0 plus 1 over 0 minus 3. So I get negative 1/3. And x is 0, y is negative 1/3. There's my y-intercept. To find my x-intercept, I let y equals 0. So I have 0 equals x squared plus 1 over x minus 3. I'll get 0 equals x squared plus 1. Negative 1 equals x squared. If I took the square root, that's a complex number, so there are no x-intercepts. My graph looks something like this. I just want us to kind of visualize what's going on. Here are some asymptotes as we describe them as limits, right? So if my function approaches an asymptote, right, and it's going to have a limit that's that asymptote, not infinity, because that's as far as it goes. The same thing holds true as x approaches a vertical asymptote. It's going to head off to positive infinity or negative infinity or change directions. Friendly reminder, there are a bunch of worked out solutions for finding asymptotes at the end of this PowerPoint. It's up on Blackboard, and if you have any questions, let me know.